So the total energy supplied in 1 hour can be calculated from the horsepower of the driver, that is motor. So we know that it is 5 horsepower machine. Then we have since we are working in joules, kg meter, we have a conversion factor of 4,500. 4,500 joules per minute is equal to 1 HP. This is in any reference book. And then we have number of minutes in an hour, that is 60. This is total energy supplied in 1 hour. Now one operation of press needs 560 kg meter of energy. 560 kg meter, that is joule in the joule. So we can now calculate the total maximum possible number of pressings in hour, so that we have the total energy, total input energy 4 into 5 into 5, 400 into 60, that divided by energy taken per operation, that is 560. So this value comes around 2410. So you can do maximum 2410 pressing operation in 1 hour. This is answer for part 1. Now coming to the second part, it is provided that the speed at start of each cycle, of each pressing cycle, of fluctuation of energy cycle. So fluctuation of energy will take on one cycle, like if you plot the kinetic energy of flywheel on x-axis and the time on x-axis and kinetic energy on the y-axis, you will see that the kinetic energy remains constant for time, and when the pressing occurs, it drops to some value, then it slowly recovers by the supply of energy from the motor. Then it again reaches constant value. So this is the mean torque that is supplied by the motor. So from this diagram, you can, like, this is the start of pressing operation. Start. From this diagram, we know that at the start of the cycle, the rotational speed is 300 rpm of motor shaft, that is collected to a flywheel. So this is flywheel rpm, and this cycle happens, pressing happens, and it then again regains its original value, then again the pressing happens. So this is one cycle. So just after the pressing is finished, you will have this point here, after just after pressing finished. So we will calculate how much is the drop of kinetic energy of the flywheel after the pressing, and from new kinetic energy after pressing is over, we can calculate the speed. So this is the approach we are going to follow. So when the pressing happens, the pressing machine absorbs energy from the flywheel, but during pressing, the motor is also supplying power, and the pressing machine is extracting power. So during the pressing, we will calculate how much the motor is supplying. So motor supply of power will be equal to 5 HP motor. Then we have a conversion ratio of 75. 75 joules is equal to 1 joules per second, or 75 watt is equal to 1 HP. So we have 5 into 75 joules per second, and the pressing operation takes 1 second. So joule per second, and this is HP. So the motor supply of power is nearly 375 joules. Now the energy required by pressing machine is equal to 560 joule, that is given quantity. So that means the supply from the motor is less than energy required by by pressing machine. So hence the excess energy will be supplied by flywheel. So how much excess energy is required by the flywheel? That is equal to energy required by pressing minus the energy supplied by the motor. Now 560 minus 375, that is equal to 185 joules. Now you know the initial like this is the fluctuation of energy. EF is equal to 185 joule. So this much will be taken from the flywheel. So this is the fluctuation of energy of the flywheel. So now you know the initial kinetic energy of the flywheel. Let's say this half I1 omega 1 square, and the final kinetic energy of the flywheel just after the operation pressing operation is over, half omega 2 I2 square. This will be equal to the energy supplied by the flywheel, that is equal to EF. So if you put the values, you know the moment of inertia of the flywheel, that is given as 60. We'll take this out common, divided by G, following our standard convention for the moment of inertia, where G is the gravitational acceleration. And then omega 1 we know as 2 pi n. So input speed is 300 divided by 60, 2 pi n by 60 whole square. And omega 2, the speed after the pressing over, is to be calculated. And fluctuation of energy is 185 joule. So if you simplify this explanation, you will get omega 2 square is equal to 10 pi whole square. This is quantity 60, and this is get cancelled. 600 by 60 will be 10 pi whole square minus 185 into 2g by 60. So this quantity will come around 926.5, and from that omega 2 will come around 30.5 radian per second. And if you want to convert it into RPM, so 2 pi n2 by 60 will be 30.5, and n2 will come nearly 290 RPM. So now you saw that n1, that the speed of the flywheel just before pressing is starting is 300 RPM, and n2 is the speed after pressing. So the fluctuation of speed is 300 minus 290, that is equal to 10 RPM. So the motor speed will fluctuate by 10 RPM during the pressing operation. So this is the answer for the part. We will now take the second numerical example. In this example, a single cylinder double acting pump is given. So single cylinder double acting pump means that you have inside a cylinder a piston, and from both the sides the pump is acting. When it moves to TDC, it pushes the fluid from this side. When it comes to BDC, it is pushing the fluid from this side. This is a double acting pump. So single cylinder double acting pump is rotating at mean speed of 50 RPM. Now the resisting torque of pump shaft may be assumed to follow a sine curve in half revolution. So in one half of the revolution, one sine wave is computed of the pump, the shaft, and the maximum value of torque occurs at 90 degree and 270 degree at value. The maximum torque value is given, that is 600 kg F meter. So since we know the peak of a sine wave and we know the period over which it occurs, we can draw the sine wave. So the one complete revolution of the pump will be 0 to 360 degree, 0 degree. Then we have 180 degree, 90 degree, 270 degree. And it is said that one half of revolution is one sine wave cycle. So obviously we'll take at 0 degree, which let's say, and the peak occurs at 90 degree. So for the peak to occur at 90 degree in a same sine wave, the value should be 0 at 0 degree, because sine 90 is equal to 1 and sine 0 is equal to 0. So the sine wave should look like this. And then at 180 again it should be 0. And again at 270 the peak occurs. So the sine wave should be like this. So like that it should repeat itself. At 270 and 90 degree we are having the peak. And this is the torque on the shaft, on the pump shaft. And this is crank degree theta. So we have got the turning moment diagram that is given from in this problem. And the maximum value of the peak is also given, that is equal to 600 kg meter. This is the maximum value of the torque, and we also know the crank degree. So we can calculate the areas and we can get the fluctuation of energy. We will consider other quantities what are given in the problem. It is required for us to find the weight of flywheel to be mounted on the pump shaft to keep the shaft speed within 1.5% of the mean speed. So here coefficient of fluctuation of speed is given, that is 1.5%. So here we are asked to find the weight of the flywheel. Actually we will find the moment of inertia of the flywheel. So here the radius of gyration of the flywheel is given. Radius of gyration of flywheel is 1.5 meter. Is 1.5 meter. And additionally, consider the moment of inertia of the shaft and gear as equivalent to a flywheel of 450 kg mass and radius of gyration 1 meter. So some additional moment of inertia is also given in this case. That is to the pump shaft mass and the gear mass and the motor from which it is driven. So the winding of the motor will also have some moment of inertia. So all this will be considered as equivalent for flywheel of 450 kg and 1 meter radius of gyration. So despite all these details, the problem is basically quite simple. You are given the turning moment diagram, T theta diagram. You can calculate the fluctuation of energy from this, and you know the mean speed. You assume some I, and you know the coefficient of fluctuation of speed. So fluctuation of speed and the fluctuation of energy will give you some I. From that I, you subtract the existing I, and you can get the I of the flywheel, the moment of inertia of the flywheel that has to be added, and you can calculate the weight of the flywheel that is required in this problem. So we'll go on solving this problem. So first we have to find the equation for torque that is necessary for calculating the area under the T star diagram. So equation of torque you can consider from this simple example. Since this is a sine wave and the peak is 600 mm, the mean will lie at the mid. So because for the sine wave, the top half and the bottom half are both symmetric. So your mean will lie at 300 kg meter torque. This is mean torque by symmetry of the sine wave. Now from the symmetry of the sine wave, if you drop a line on the x-axis, you will find that they are occurring at 45 degree and 90 plus 45, that is 135 degree. So this is also from the symmetric sine wave, 0 to 90 degree, cutting in between, it will cut at 45 degree. Now the fluctuation of energy is the area above the mean torque line. and the same area is also below the mean torque line from the symmetry of the sine wave. So we have to basically calculate this area. So first we will write the equation for the torque. Normal sine wave looks like this. It starts at like the midspan starts at 0 degree. So in this case, it is starting at 45 degree. So in normal case, you have the amplitude A. Let's say the equation of the sine wave is A sine theta. Okay. So in the present case, since the wave is starting at 45 degree, the theta will change by minus 45, that is pi by 4. And amplitude in this case, since the mean is 300 and the maximum is 600, the amplitude is 300 of the wave. So the equation for torque will be 300, that is amplitude, multiplied by sine theta minus pi by 4. And this fluctuation is happening about a mean. So the mean value is 300 of torque, and about that the 300 sine theta fluctuation is happening. So actual equation for torque is 300 sine pi minus 4 plus 300. So if you simplify this expression and arrange trigonometrically, you will get the final expression as 1 minus cos 2 theta. So this is a derivation I leave it to you. It's a simple mathematical trigonometric derivation. Now for calculating the fluctuation of energy, we have seen that it is given by the shaded area in the above diagram. So this shaded area is getting, you can integrate the sine curve from 45 degree to 135 degree, and we can get the shaded area. So, and then we have the equation for torque. We have to subtract the mean value, 300 out of that. So it will be fluctuation of energy will be shaded area. It will be equal to integration from pi by 4 to 3 pi by 4 of 300 1 minus cos 2 theta, that is the actual equation for torque, minus 300, that is the mean value d theta. So this will be equal to integration from pi by 4 to 3 pi by 4 of minus cos 2 theta into 300 d theta. This will be equal to 300 into minus sine theta by 2 integration from pi by 4 to 3 pi by 4. This will come around 300 kg meter. So 300 joules is the fluctuation. Now since we know the fluctuation of energy, that is EF is equal to 300 kg meter. So now we will use the formula for fluctuation of speed. So EF is equal to I omega square Ks. So Ks is the coefficient of fluctuation of speed. So you know EF is 300, I we have to calculate, omega we need the mean speed, it is 2 pi, and the mean RPM is given as 50 by 60, 2 pi in the 60, this will be equal to 5.233 radians per second. So you can substitute this value here, 5.233 square, and coefficient of fluctuation of speed, this we know it is given as plus minus 1.5%. So the speed of the shaft can vary within plus minus 1.5%. So max minus min speed of the shaft can vary within 3%. This is 1.5 given, positive and negative. 3%. 3% is equal to 0.003. 0.03. Right. So this value was put here 0.03. So I will come from this calculation as equal to 365 kg meter square. Now we have to calculate the flywheel of the moment of inertia of the flywheel. So we have the moment of inertia of existing component. So existing component are given as I of let's say IV existing component, that can be derived from a mass of 450 divided by G, uh, concentrated at 1 meter of radius of gyration that was given in the problem. The existing component have nearly 46 kg meter square of moment of inertia. So the moment of inertia needed is I flywheel that we have to add to keep the fluctuation of speed within the limit. This will be equal to I required minus this is additional I needed. So this is actual I required minus I existing. So this is 365 minus 46 and this is 319 kg meter square. So moment of inertia flywheel that you have to add is 319 kg meters. 319 kg per meter, kg meter square. Now the radius of gyration is provided as 1.5 meter. So the mass of flywheel will be equal to I by k square, radiation of gyration square, because I is equal to mass into k square. So we have 319 divided by 1.5 whole square. This value will come around 142 kg. So this much mass of flywheel you need. The problem it was asked the weight of flywheel. So this you can calculate by 142 divided by G, that is 9.81 equal to 1390 Newton. So this is the answer. In both of the problem that we have considered till now, there is no variation from the supply. The supply is from a motor that is applying constant torque, and the variation is coming from the output, the load. So in the first case, the variation came from the punching pressing machine, and in this case, it is coming from pump. So the fluctuation in load is basically what we will be calculating while doing the calculation of the flywheel. And the same principle applies if the load is constant and the in supply is fluctuating, like in the case of IC engine or steam engine. So now we consider one more numerical example related to the flywheels. So here the problem given is that a machine shaft runs at mean 200 rpm and it requires a torque. So the load is such that the torque requirement is such that it increases, the torque increases uniformly from 700 Newton meter to 2100 Newton meter for first quarter revolution. So quarter revolution means pi by 4. So 0 to pi by 4 it uniformly increases from 700 Newton meter to 2100 Newton meter. Let's say this is 2100 and this is 700. And so 0 to pi by 4, first quarter revolution, it increases. Then it remains constant for half revolution. That means half revolution is pi by 2. So pi by 4 to pi by 2, that is 3 pi by 4. So it remains constant. Here somewhere you have pi by 2. It remains constant. And after 3 pi by 4, it reduces to 700 Newton meter in next quarter revolution, and then remains constant for another half revolution. So from 3 pi by 4 to quarter revolution will be pi, 3 pi by 4 to pi. It will reduce again to 700 and then it will remain constant again for half the revolution. That is pi to pi by 2, that is 3 pi by 2. So our torque cycle is defined After 3 pi by 2, the same cycle will repeat. So here you can see this is a non-standard cycle. The once the cycle is completed the in 3 pi by 2 revolution. So degree of rotation of the crankshaft. So it is not necessary in the flywheel calculation or any calculation that the cycle should cover 2 pi. In 3 pi by 2 also, if one cycle is getting completed, we can calculate for that. So we consider only this much portion of the cycle which is coming from 0 to 3 pi by 2, and one cycle is done and then same thing is repeated. We will analyze only this much portion. Now the other parameters given in the problem are: it is provided this shaft is supplied by a motor of constant torque, and the rotor has the weight of 4500 Newton and radius of gyration of 0.3 meter, and it is desired to limit the maximum speed fluctuation within 3% of mean speed. So this will be accomplished by providing an additional flywheel. So by adding a flywheel in the given system, we know the moment of inertia, we know the load cycle, and the torque is constant. We add an additional flywheel whose mean rim speed is limited to 1.08 sorry 1080 meters per minute. So this requirement comes from the side of the stress in the flywheel rim, the hoop stress. We know that it limits the maximum velocity because stress is rho v square. Rho is constant for a material, and v square is what limits the circumferential stress. So we know the stress limit of the flywheel that is dictated by the maximum rim velocity. So the problem asked is that find weight of flywheel rim.